recording. Good evening, class. Elementary statistics, practice test number 5, module 5, covering chapters 10, 11, and 12. Here's chapter 10, correlation and regression. Chapter 11, goodness of fit and contingency tables. Chapter 12, analysis of variance. We are looking at chapter 10, correlation and regression. Could somebody read question number 1 for us, please?
Given the sample data, find the value of the linear correlation coefficient R. Test the claim that there is a linear correlation between the two variables x and y using both method 1 and method 2 with alpha of 0.5. Find the regression equation and find the best predicted value of y when x is equal to 2.
Excellent. So let's just recap the concept of correlation. Scatter plot and the strength of the linear correlation are. A scatter plot is a graph of the ordered pairs x comma y. X is normally the independent variable and y is the dependent variable. When you have a pair, the first one is the independent variable. Here's the shape for a positive correlation. Could somebody read this, please?
Scatterplots and the strength of the linear correlation are. A scatterplot is a graph of the ordered pairs x and y. X, the independent variable, and y, the dependent variable. A, distinct straight line or linear pattern. We say that there is a positive linear correlation between x and y, since as the x values increase, the corresponding y values also increase. If there is a strong positive linear relationship between the variables, the variable of r will be close to positive 1, 0.7 or larger.
Here's the shape of a negative correlation. Could you read this, please?
Distinct straight line or linear pattern, we say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease. If there is a strong negative linear relationship between the variables, the value of r will be close to negative 1, negative 0.7 or smaller.
And as you can see, there is no correlation and there is no distinct pattern, which suggests that there is no correlation between the two variables x and y. Generally speaking, when we are close to 0, it's considered to be no linear correlation. When we are away from 0, either close to positive 1 or close to negative 1. So R has a value between negative 1 and 1, and normally 0.7 or larger is considered strong, also negative 0.7 or smaller, close to negative 1. And of course, correlation doesn't imply causation. That's extremely important. Now, nobody expects you to do this by hand. On purpose, this is a very small set of data, so we can see how it's done by hand. As you can see, the formula for R, the linear correlation coefficient, is n summation of x, y, minus summation of x times summation of y, the square root of the brackets n summation of x squared minus summation of x quantity squared times the second bracket n summation of y squared minus the summation of y quantity squared. It's a pretty complicated formula, and that's why nobody expects you to do this by hand. However, because n is extremely small here, we have only just 4 pieces of data. Let's see how we do this by hand. So we need to write x and y, and then calculate x times y, x squared, y squared. Let's do that. So here's the column x, here's the column y. When we say x times y means multiply these two. 1 and 2 gives you 2, 1 and 8 gives you 8, 3 and 6, 18, 5 times 4, 20. What is x squared? The very first column. Square it. 1 squared is 1, 3 squared is 9, 5 squared is 25. What about y squared? The second column. Square it. 2 squared is 4, 8 squared is 64, 6 squared is 36, 4 squared is 16. Finally, we're going to make up a row and add them up. In other words, summation of x, that means 1 plus 1 plus 3 plus 5 gives us 10. The same thing happens for each and every one of the columns. So, notation-wise, this is summation of x, summation of y, summation of x times y, summation of x squared, summation of y squared. Now, all we have to do, plug into this formula. N, which is 4, summation of xy, which is 48, minus summation of x, which is 10, times summation of y, which is 20, that would be the numerator. The denominator inside the square root, the first bracket n, that means 4, summation of x squared, that means 36, minus summation of x, that means 10, and then square that number. Second bracket again, n is 4, summation of y squared is 120, minus summation of y, which is 20, squared. That's exactly what we have. And it will result in the following number. All we had to do in part A, find R. As you can see, it is extremely tedious. Nobody expects you to do this by hand. It is done by technology. Any technology of your choice will do that. As an example, for a TI calculator, first you want to clear the list, such as L1. Here's the command for that. And then you run the linear regression test as follows. So first, the first column and the second column are the X and Y. L1 and L2, the first list and the second list. And now you run this command on a TI, linear regression t-test, by going to stat, test, so on and so forth. When you do the math, it gives you a lot of information. For this part and this part only, we are interested in R. There are other information, we'll discuss it in a moment. And it depends on how many decimals you want. For example, if we want to stay with the third one, then 4 changes to 5. And again, you can use any technology. This is one of the common ones you can use online, free technology. The second part is asking for the test of hypothesis. Test of hypothesis has 4 parts. Null and alternative hypotheses, as far as I'm concerned, test statistic, distribution, make a decision, and from the previous page, we have the value of n and lowercase r. And here's how the first step starts, which is universal H0, rho equals 0. H1 rho is not equal to 0, which makes it a two-tailed test, and that is the claim. That means we are interested in whether there is a correlation or not. If we reject H0, then there is a correlation. Remember that. We want to calculate the test statistic. I want you to pay attention for the t-test. The formula is R. minus mu sub r over the square root of 1 minus r squared over n minus 2. Please take a look at this formula and convince yourself they are the same. I hope you see this is a complex fraction, And by the way, mu sub r is always 0 for us. This is really rho is the same as mu sub r, correlation coefficient for population. And you don't even have to write that, just go with r. Now that you have r only, I hope you see that you can flip this over and put n minus 2 at top over 1 minus r squared. Why am I giving you both formulas, which is ultimately the same? Depending on the text, you may come across a different one and you think, oh God, they are different, and they are not. Plug in, we have everything. We have lowercase r, we have n, and we end up calculating this complex fraction giving us the value of t. Test statistic using the t distribution results in this number. Bear in mind, we are doing it by hand. If you do it with the technology, they use more decimals. It might be slightly different. The second method, the test statistic, just uses the R. So I want to show you both methods next to each other. Distribution, CV, critical value, RR, rejection region, NRR, non-rejection region. Using the t-test alpha of 0.05, degrees of freedom is n minus 2, in this case, x and comma y. So n minus 2, it becomes 2. From the t-table, we get plus minus 4.303. And if we go with the second method, n is 4, alpha is 0.05, and we use r, the critical value from Pearson correlation coefficient table. You do have that table in the Canvas, and it's one of the last tables. From there, r becomes plus minus 0.950. I'm running in parallel. Now we are going to go with the graph. And what I'd like you to see is that if we stick with this method, take a look at this one. We are looking at the t-test. The critical values are plus minus 4.303. And the test statistic is negative 1.927. It's right in the middle, and it means way into the non-rejection region. If we go with the t-test, do not reject H0 or fail to reject H0. What about this one? We use a number line. Negative 0.950 is here, positive 0.950 is here. And the test statistic is the value of R. It's in the middle, and it's way into the non-rejection region. They both should, must, and they do give us the same result. Fail to reject H0. So if you're not rejecting H0, what are you rejecting? H1. So you're rejecting the correlation. That's the idea. There is no, so the claim becomes false. There is no linear correlation between the two variables. What I'd like to show you again, just to remind you about the table, both tables, how they work. So if you're looking at the t-test, alpha is 0.05, degrees of freedom of n minus 2, 4 minus 2 is equal to 2. And so you look for the left column of 2, top area in 2 tails of 0.05. When you put the two together, you end up with this number because you know it's a two-tailed test plus minus 4.303. As for Pearson correlation table, N is 4, alpha is 0.05. And it's important to know that you're dealing with alpha 0.05 because otherwise it makes a difference. So put the two together and you see 0.950 because it's a two-tailed test plus minus. Again, I'm showing you in case you're using the table, how you come up with the answer. As far as the regression equation, since we have all the information from the first page, I'm going to give you the formula. In essence, you're dealing with y equals mx plus b, slope-intercept form. I want you to know that from elementary algebra. So y hat is b sub 0 plus b sub 1 times x, or y hat is a plus bx, depending upon the technology. They may use this. This is, for example, the one that is used in TI. The slope is calculated as b1 equals n summation of xy minus summation of x times summation of y n summation of x squared minus summation of x quantity squared. The y-intercept, or b sub 0 in this case, is y bar minus b1 x bar. Y bar is the good old average for y, summation of y over n, and x bar is the average for x, summation of x over n. Again, none of this is done by hand for this question. Since we had a small data, let's do it by hand. So we're going to put this into B1. All of this we have, and we put it into B1. N is a 4, summation of xy is 48, minus summation of x times summation of y, 10 times 20. That's the numerator. N times summation of x squared, that means 4 times 36, minus summation of x, which is 10 squared. Simplify, you come up with this answer. Now, to come up with b sub 0, let's calculate y bar and x bar simply by dividing summation of x by 4, summation of y by 4, because n is 4. And we got those values. So this summation divided by n gives us, this one gives us x bar, this one gives us y bar, and let's go with this formula, which says b sub 0 is y bar minus b1 x bar. Let's plug in, we have everything. So by the way, we have done the rounding. You want to use a lot more decimals when you do your calculation here. Notice on purpose, I put a lot more. And so that's b sub 0, that's b sub 1, and we're going to put it into a formula, and that is our regression equation, which we will not do by hand. And in fact, I'm going to show you the first page when we did this calculation. These are the two numbers we need. Take a look. A and B, they are given to us. So you don't have to do this by hand. When we ran the linear regression t-test, we ended up with everything we wanted, including those two. And by the way, look at the degrees of freedom also, which is n minus 2. A couple more things here I'm going to add in a moment, but let's continue with this regression equation. Find the best predicted value of y when x is equal to 2. That is the purpose of the regression equation. We want to do the prediction, and we always use that formula if we prove that there is a linear correlation, but we proved there is none. Therefore, we can't plug in and predict. In that case, we use y bar. Since we proved there is no significant linear correlation, the best predicted y value is simply y bar. Now, what I want to add here, a couple of things. Notice the other things that they have calculated for us. T, this is the test statistic. Okay, it's negative. So the area to the left of that, because it's two-tailed test times 2, and that ends up being this number. As you can see, this number 0.8, let's say we stop at 5, is way larger than alpha 0.05, which gives us the same result. Do not reject H0, no linear correlation. In other words, what I'm saying, if you are using technology, you want to use the p-value with the t-test, and the p-value is larger than alpha 0.05, giving you the same result. Again, what I want to emphasize is that the best predicted value is y bar because there is no significant linear correlation. Could somebody read this question, please?
A researcher is studying the effects of testosterone injections on different lab mice. She controls the concentration of testosterone injected into the mice and measures their metabolic rates. Analyze the following data sets. Will you be running a correlation or a regression? A, find the value of the linear correlation coefficient R and test the claim that there is a linear correlation between the two variables X and Y with alpha equals 0.05.
Perfect. First and foremost, we are going to run a regression. Since she controls the concentration of testosterone injected into the mice and measures their metabolic rates, it has to be a regression, which gives us the first step of test of hypothesis. I want to go over all parts. H0, rho equals 0, HA or H1. In many cases, they use HA instead of H1. It's the same thing. Rho is not equal to 0, two-tailed test. Now, what do they mean? The first part means there is no correlation. So H0, rho equals 0, there is no correlation. And the second part means there is a correlation. So what do we mean by there is no correlation? We mean there is no correlation between the concentration of testosterone in mice and their metabolic rates. In this case, we are saying basically the same thing, but there is a correlation between the two variables. So now we have a set of data. We run technology however we like it, whatever is available to us. This is obviously not done by hand. And when we go through it, I am giving you some information from Excel. Here's the value of R squared, and there is more information here. And I'm going to tell you exactly what they mean in case you run something like that. All right, so we are looking at the same question. We have the following information. And here's the Excel run information. N is 17, R is 0.9934, R squared, which is the square of this number, is 0.9869. And we wrote the very first step. Now let's go with test statistic. We go through the process of calculating it. Here's the formula. However, we have this number, which is this one. So T stat. So this is, in case you're running Excel, here's the number. As far as method 2, you just use R. Again, you have that one also. The next one is the critical value. However, technology gives you the p-value. Based on the t-test, the p-value is found here. So when we see this number and then e minus 15, that means times 10 to the power of negative 15, which is practically 0. It means from this decimal, go to the left 15 places, practically 0. And with that, the concept is test statistic is way into the non-rejection, rejection region, and you want the area to the right of that times 2. We want the area to the right of that times 2 because it's a two-tailed test. If we were to go with the second method, any 17 alpha is 0.05 and the critical value would be plus minus 0.456. This comes from the Pearson correlation table. This is from the same table we discussed earlier. As you notice, this number is way larger than positive 0.456. So if you go with the test statistic or if you go with the p-value, makes no difference. This is way less than alpha of 0.05. You are going to reject H0. So the decision is to reject H0. Why is that? Going back to the technology, the calculation that gave us this p-value, it's way less than alpha of 0.05. We're going to reject it. If we want to go with the second method, also this number is way larger than 0.456. So if you are rejecting H0, then what are you accepting? Loosely put, HA, the claim becomes true, and therefore there is a significant linear correlation between the two variables. What does it mean? Therefore, we conclude that there is a significant correlation between the concentration of testosterone in mice and their metabolic rates. Since this is a regression study, the significant slope suggests that the increase in concentration of testosterone in mice causes increase in their metabolic rates. Again, the beauty of stats at work regarding science. We are looking at the same question. The next part is asking for the regression equation. So let's see if we are given that. Take a look at what the technology gave us. That's the intercept. So clearly, y hat is 199.059x plus 379.493. Technology gives us everything we need. Find the best predicted value of y, namely metabolic rates, when x is equal to 1.3, the concentration of testosterone. Now, because we proved there is a significant linear correlation, we simply plug in. Bear in mind, we did not plug in the previous example. There was no correlation. Now there is a correlation. You plug in, and this is the predicted value, 638.2697. The last part of the question, using the above pairs and the value of R, what proportion of the variation in metabolic rates can be explained by the variation in the concentration of testosterone? In general, it's always R squared. If R is given, you square it. Sometimes they give you both. The technology gives you both. So simply put, the answer to the question is the value of R squared. 98.69% of the variation in metabolic rates can be explained by the variation in the concentration of the testosterone.